So let's start talking about encoding the Booth pairs even further. So an acute observation would actually be that Booth pairs can be represented in terms of even sparser bit pairs. Um, you can group two Booth numbers into bit pairs, and they have equivalent numbers for them. So basically, you can have these where 0 0 becomes 0, 0 1 becomes, well, 0 1, which is positive 1, 1 minus 1. So a 1 in the higher bit and the negative 1 in the lower bit just becomes a 1. This is, you've seen me do this before. A 1 in the higher bit with a 0 in the lower bit is just a 2 in the lower bit. A negative 1 in the higher bit is a negative 2 in the lower bit. A negative 1 in the higher bit plus 1 in the lower bit, so that's negative 2 plus 1 becomes negative 1. A negative 1 in the lower bit is still a negative 1, and, well, 0 0 becomes 0. So you'll see more examples of this um, later. But basically, you multiply um, the the number in the higher number counts for 2, and the number in the lower number counts for 1, and then you add those together, you get the bit pair. So you have here in bit pair encoding, you can turn this into 0 minus 1 2. Let's see how we do that. In Booth notation, you have 0 here for negative 6, by the way. You have a 0 here. You have a negative, you have here a negative 1 and a positive 1. And then you have here negative 1, a 0, and the positive 1 again, going on to infinity. And what you have here is actually these two become negative 2. These two become negative 1. That's negative 1 times 2 plus 1. And then these two become a 2, actually. But I forgot. Okay, if you're doing Booth representation, you throw away the last 1 because that's the sign bit. So actually, you just have a 0 right here. So in terms of bit pair encoding, you have those. That's 0, 1, 0 minus 1 minus 2. And then to do the partial products, when you multiply by 2 in terms of binary, you actually just shift by one place. So here you have 0, 1, 1, 0, 1. Now if you negate that, that becomes 1, 1, 0, 1, 1. And then times negative 2, that actually becomes 1, 0, 1, 1, 0, 0, 1 over here, because it's shifted by 1. So this is times negative 1, and this is times negative 2. So when you multiplied it by negative 2, this is the partial product that came out. That's 1, 0, 0, 1, 1, and the 0 because you shifted it once. And then you copy the sign bits because it's a negative number. Next, the partial product is a negative 1. So you don't shift, but you still use the negative version of the multiplicand. And then you have a 0 partial product. And note that for bit pair recoding, you have shifts by 2 instead, because the bit pairs are now, well, bit pairs. So there's a blank space over here, so you don't have partial products over there. But you can also think of it as putting zeros in between. And then with that, you can add the partial products to get the final answer of negative 78. You can see that we have a negative and a positive number here, but we don't care because we're using a recoding method. We know from Booth that the recoding method makes it so that you don't have to think about the signs. You just have to think about the signs of the partial products. Now let's talk about ripple addition. This does not particularly have anything to do with the Booth algorithm or the bit pair recoding, but you see, this is how we implement adders, actually. Well, at least in a straightforward manner for now, we can implement addition of 3 different numbers by doing this. So we if we assume that we don't have a carry in, you can use a half adder, which is basically a full adder that doesn't have a carry in. So there's no C in right here. That's why it's a half adder. But basically, you can use an initial set of adders to add each of the bits of P and Q, and produce carry out bits from there. And the carry out bits, well, of course, they go to the next adder down the line over here. But the sum bits, we actually pass that over to a next layer of adders, where where the bits of the next number to be added are put into the addition, whose carries are also passed along the line. And the two carry outs from the first layer and the second layer are then added over here at the end, where we get S3. We actually have a carry out as well over here, which is sometimes actually a carry out. So sometimes we will need to take that into account, but for say partial products of multiplication, this carry out will never be 1. So you don't have to worry about that for if you're adding partial products of multiplication. If you're not adding partial products of multiplication, then you will have to think about this carry out bit. Okay, now you can see here, okay, in this previous slide, the critical path of the circuit is actually 5 adders. So here, let's say I am Q0, I need to traverse this path into here, into down here, into down here, and then over here, for a total of 5 adder delays. If, for example, a bit change in Q0 caused a bit change in S3, that's the entire delay. It would be 5 adders of delay for us to get into the either carry out or S3, and that's the critical path of the circuit, which is kind of bad. So we're going to introduce another topology to the circuit, which is carry save. So we can think of full adders are actually or of the carry in of a full adder as actually an extra operand. So what you have now is you add P, Q, and R all in the same first layer. And then what happens is that the carries from the first layer are then passed to the second layer instead. So you can see here. So it's basically the equivalent operation. It's just that the carries are now passed to the second layer instead of being passed again to the second layer. And you can see here that it improves the critical path, because you know the carry and in the same column rather. So you can see here in the same column, um, these bits and the carry bit are all the same, because you just add them together as well to get the actual sum. And then the carry out is also still the same, no matter which of these are connected to what. So you can connect this to that, or you can connect this to the bottom. It's still the same. Or if there's a carry in for this half adder, you can actually even put that in there. But the thing is, all of those are equivalent. So if you wire them up like this, then you get a shorter critical path. You can find it from R0 right here. So if I am R0, I go through this full adder, and then this half adder, and then this full adder again, and then this half adder all the way to S3. So the critical path is now 4 adders. And this critical path will only improve more and more as the number of bits of the addition gets higher. So since it's less than n, then it's better than the normal carry, the normal ripple carry adder. So we can make the construction of carry save networks actually systemic by grouping the addition operands in terms of dots. So for example, our problem is we have to add 4 numbers, 4 3-bit numbers, N, P, Q, and R. So um, the ripple implementation will have 3 levels, and the critical path would be 6 adders if we so chose to have a ripple carry implementation of this one. But instead, you can have a carry save adder network for this one, where you add 3 bits at a time. So how do you do it when you represent them in terms of dots? Now you can see it right here. So every three inputs, you can this is N, P, and Q. So this is N, P, and Q right here. Every three bits of this can be added together. So using one full adder. So you group these three, and you get a full adder, which produces a sum bit and a carry bit. So the carry bit is represented in gray here, but my pen is just blue, so I'll just say C for carry bit and a non-filled dot for the sum bit. So basically, you get three sum bits and three carry bits, which we put down here. So we have three sum bits; these are white, and three carry bits, which go on to the next column. So this thing has to go to the next column. The carry bits go to the next column, so these carry bits are now in the next column. But basically, this is the thing that you want to add. You want to simplify next with the carry save network. So let's group those. So two operands means half adder. There's no carry in. Three operands. These are full adder and full adder. So you can see here we put them in as full adder, and half adder. If you remember correctly, the black dots are the R operand. So we now introduce those as well for this layer. So here you have also the carry bit that, if you remember, came from this guy. So this guy also has this carry bit, and well, that guy has that carry bit. So so this white one is this one, and then since this gray carry bit came from this one, you wire that there, and then you wire this one there as well, because this gray carry bit came from this guy. And now that produces white, gray, white, gray, white, gray, and this is also still the gray from before. You know, remember gray, the carry bits shift by one to the next column. So now you have white here, gray there, white here, gray there, white here, gray there, and then this is still the very old gray that we haven't touched yet. This one. So the final stage of the ripple carry, we don't have any more simplifications after this. You have three half adders because there's only two operands. And basically all you do is you add the sum bits from the respective column. So this is the sum bit, this white thing is actually this thing. This other white thing is actually this thing. And then you add that to the carries from before. So this is the gray carry over here, and this gray carry is this one. And then the two carries is the one from the first layer and the one from the second layer. And those produce S3 and S4 respectively. And since this is the final layer, we actually just do a ripple carry over here now. So I'm sorry, these are not full adders. These are now full adders because the carry of this thing goes into here. That's why they have three operands. So when it's the final stage, 2 does not become a half adder. You make them full adders in order to make them a ripple carry adder, so that you only have three layers as well. Because it doesn't make sense to make it to like still have more stages afterward just to propagate the carry bits. But that's it for the construction of the carry save network for that particular example. The critical path of this network would be one that starts from Q0. So that's 1, 2. Okay, never mind. From Q0, that's 1, and then 2. Okay, that's 1, 2, 3, 4, 5. So it's this lower path that's the critical path, which goes through 5 others. Which, as you may know, as you may have seen, is better than the 6 adders of the ripple carry adder implementation that we saw earlier. Now, for partial operands, you can see here we're going to build a so these are partial operands of multiplication. How do we know that? Well, you can see here they're shifted by 1 every time, so one could probably assume they come from multiplication. But basically, if we apply that algorithm to the carry save, you have, okay, you can group two each, or up here. You start from over here, by the way. So you start looking from here to here, and then you encounter a group of two, so you group them by two already immediately. But basically you can group these by two, and you get half adders over here. um well they call it N P Q R. So those are the partial products we are adding. We're adding partial products N, P, Q, and R. We have half adders over here. They produce some bits, the white ones, and carry bits, the gray ones. And then we group those again by threes this time. So this full adder adds a carry bit from before, a sum bit, and then one of the partial operands, Q0, and then Q1 here, and then Q and P here along with the carry from before. So that's this full adder over here. And then that further simplifies the network. This thing produces a white sum bit and then a gray carry bit. So we get three white sum bits and three gray carry bits from these three full adders, which you can then further add with three full adders, which are over here. And the next stage, that turns them into three white sum bits and three gray carry bits, and then you group those into two to get the ripple final stage, which is a half adder and two full adders, because this is the ripple carry final stage. So you use the ripple carry format instead, and then that produces the entire sum, as you can see here. So from S0 to S7. And we actually have for some implementations like this one, so you don't have to stop by you don't have to stop by just grouping every twos. You can alternatively add N, P, Q, and R in terms of five already. So that's group these by two. So that's half, full, 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 half. So if you do that, you get a string of sum bits and a string of carry bits. Well, five of them, because you have five right here. And you have these guys left over. And then you can turn those into a layer as well. And then they turn into themselves a string of white sum bits and gray carry bits. And then you can use that as the final stage, where you just ripple the carries to each other. That's one. So then you have the half adder first stage, and all of these are full adders until this one, which is only a half adder. Why is it only a half adder? Because you only have the carry plus the carry from here plus the carry from the last layer. So this one and this one becomes S7. So here. And because this is a half adder, we're supposed to have a carry out, but it will always be zero for multiplication. So that's that's a simplification we're going to do by knowing what to expect from partial products.